Hi, hello. Let's take a look at our lab 2, which is working on the Newton's second law, and we're dealing with a dropped ball from rest, and it falls slowly. And we have two computational models. The first one, we have a dragging force. No, I mean the first one we don't have a dragging force except on the ball. We only have a weight. And for the second computational model, we have a dragging force, which is exerting upward towards the on the ball, and we also have a weight, and we also have a real life experiment video. But firstly, let's take a look at the formula for today's lab. We know that in Newton's second law, F net is equal to weight plus F drag if we have it. And V final is equal to V initial plus acceleration times delta t. And since delta t is small, we can, in our displacement function, we know that Rf is equal to V final times the delta t. And let's firstly take a look at our computational model, and then I will show you the experiment model. So this is a code for computational model one. We do not have a dragging force. We have F net divided by the mass of the ball, which is equal to our acceleration. And as I mentioned before, the position position the position function is equal to position plus initial position plus velocity times final times delta t. And for the second computational model, we know that we have a drag force, so we only add drag force here in our velocity function. And for the drag force, we need to get the speed of our ball. Since the ball is falling downward, you can only get the y component of the ball and square it. And b is our constant. Let's take a look at our result. So this is a result for my model one, which is where the dragon force is not included. We can see that the speed is decreasing, and this is computational model 2's result. You can see that the velocity will be constant at the end. And let me show you my real life experiment. So my roommate is holding a ball, and this drops from somewhere and finally hit the ground. And I recorded the data. We can see that so the blue one is my real life experiment. You can see, and the orange one is my computational model one. So both of them do not have a drag force, but actually for the real life experiment, we have an area resistance force, but the time is so short. The final air resistance force is not equal to the weight. So the graph of the computational model one is similar to the real life experiment. However, for the computational model two, you can see that it finally becomes a straight line because the dragging force finally equal to the gravity force, and the net force is equal to 0, so we don't have an acceleration. And we cannot answer the first question, but you can now answer the first question, because basically it's what I mentioned before, like because you can see from the spreadsheet, we have a consistent model from computational model one and the real life experiment, and the object is dropping in constant way only if it has a dragging force. For question 2, let's show you my new model. Here, this is the result, and I modified the code, so we would have a F forward, which is the F initial, and since F initial only increase the initial velocity, so dragging force may still finally equal to the F weight. So you can see from the result, the final velocity is larger. I mean, the absolute value of the following velocity is larger than the previous computation models, but it will still finally become constant. So it's larger, but it will still be constant. And thank you. That's all the things for today's lab.